No, this is the same guy.
Right, so we're looking at examples of different types of estuaries based on their stratification. We talked about the salt wedge and the strongest stratified. Then we have a diagram here of a partially mixed estuary in which the layers, the light water layer and the heavy water layer, are less distinct because of stronger mixing, because of the larger tidal input and the smaller river discharge relative to the previous examples. And an example of this is Chesapeake Bay. If you look at the distributions of salinity along the estuary, salinity, temperature, and density anomaly in the lower. I was going to ask you, where is the head of the estuary? You see, you can see the mouth is on the right. But that's where the, why is the mouth on the right? Given those distributions. These are longitudinal sections. Yeah. Does it make sense that it's at the mouth? The higher salinity water, the oceanic salinity at the mouth, heaviest. And notice that the density follows the salinity very closely. The salinity plays a lesser role in the density of the water. I think we've talked about this, but does anybody remember why the salinity is more influential in the density in estuaries than temperature? Remember, it has to do with the thermal expansion and the saline contraction. And the saline contraction is 4 times greater typically than the thermal expansion. For those of you who took the class last semester, my class, you generated those contour plots of thermal expansion and saline contraction. So I would have thought that, I hope that you learned something from drawing those. I didn't understand the concept until I drew those contours myself. So hopefully you got something else. Okay, so there's the typical distribution of a partially mixed estuary with the salty water trying to intrude but mixing intensely. If it was a salt wedge estuary, this red would intrude all the way in. And the light water, the blue water trying to go out of the estuary at the surface. Then the well-mixed estuaries that are more difficult to observe actually. But schematically they have, they're laterally stratified instead of vertically stratified, so to speak. So there are lateral gradients instead of vertical gradients. You can see the river diluted water trying to come out on the right side when you look out toward the ocean, and then coming in on this side, the ocean water coming in this side. And that's because of the effects of Coriolis. But again, I insist that this is in the northern hemisphere. So keep that in mind. And again, like I said, there are very few examples of this, but the Chesapeake Bay may behave like a well-mixed estuary in the fall when there's no fresh water input and when there's a lot of cooling and a lot of wind mixing. So this is the distribution of 3 variables that we're looking at. We're looking at a transect at the mouth of the Chesapeake Bay. The transect is here in the lower part, and we're sitting in the Atlantic Ocean looking into the estuary. And the 3 variables that we have are salinity, which are the dark contours, temperature, the white contours, and density anomaly, which are the color field contours, the shades of color. And you can see that over the shallow areas, the water column is essentially mixed, right? There's very weak stratification in the deep part, in the channel. We later on talk about why there's stratification in the deep part and no stratification over the shallow part. But you can see also that the light water is leaning toward the left as we're looking into the estuary, and the heavy water is appearing more toward the right because as we're looking into the estuary. Again, this is because of Oreo. All right, so we've talked about, up to now we've talked about typical estuaries and the most widely studied estuaries, because they're in temperate regions, and that's where the developed nations are and where research takes place mostly. But lower latitude estuaries, where underdeveloped nations are found typically, there's less research going on there. So we know much less about tropical and subtropical estuaries than temperate estuaries. So we can classify estuaries in a different way by looking at their water balance. In this case, we have two different situations for the same type of estuary, in which we have an inverse type of estuary. So this is the more frequent reason of why there's an inverse estuary. There's an embayment here attached to the ocean, and the salinity inside. What's going to happen to the salinity inside the basin when there's a strong evaporation and no precipitation or no river discharge? That's salinity 1 will become larger than salinity 2, right? Temperature 1 will also be larger than temperature 2, but we know that salinity controls density when the changes of salinity are large. So if there's, let's say, a difference between the salinity here and the adjacent ocean of order 1 or larger, then this water will be heavier than this one. So if this water is heavier than this one, what's going to happen? That the heavier water will sink, as shown by this arrow. Near the bottom, the water will go out of the estuary near the bottom and into the estuary at the surface. So this is the inverse situation that we have on the regular type of estuaries, in which light water goes out at the surface, heavy water comes in at depth. Here we have the opposite, right? Heavy water coming out at depth, lighter water coming in at the surface. In this case, the light water has salinities close to 35 also. What happens is the heavy water has higher salinities, higher than 35. So this happens in subtropical regions. It is possible that the St. Augustine Inlet nearby may exhibit this type of situation, this type of circulation at certain parts of the year. So we need that. This is an open question that's open there for you guys to explore. So that's an example, because think about that range of latitudes throughout the world and closer to the equator. There are many systems that might show this type of behavior, where semi-closed systems that have high evaporation and show inverse estuarine circulation. Another case in which the water inside the basin becomes heavier than the water in the ocean could happen if there are no salinity differences between the basin and the adjacent waters, but there's intense cooling. If there's intense cooling, then the temperature inside the basin will be much lower than the temperature outside, right? Because it has a lower heat capacity. It loses heat more rapidly. It's shallower, so the water becomes heavier, and it will tend to go out of the system near the bottom, whereas the adjacent water will come into the system at the surface. So you might have a situation like this, again, in subtropical regions during the winter when you have intense cooling. An example of this has been reported in Australia, but I'm sure in Florida also we might have this type of. So we haven't looked for them, I guess, hard enough. That is, we haven't studied them enough. But in this area, in Florida, I think we can have these two types of systems, at least parts of the year, which makes them even more interesting that they switch from one type to another during different parts of the year. So again, based on the water balance, estuaries can be inverse estuaries or positive estuaries or normal estuaries. An example of a system that switches from an inverse to a regular estuary depending on the time of the year This was the example that I mentioned, being a tectonic origin. This is the Bay of Guaymas, and it's in the mainland side of, in front of the peninsula of Baja California in Mexico. So there's the Bay of Guaymas. There's a zoom in the Bay of Guaymas. Very shallow area, average depth of 2 meters, but there's a channel here that's 13 meters deep. That's maintained by dredging because there's commercial, there's ship traffic, there's a harbor there, commercial port. But if we look at a section right here, at this section at the mouth of the bay, this section, and we're sitting here looking into the bay, you can have this type of exchange. These are isotachs, which represent lines of flow. So in the upper panel we have water going away from us. Again, we're looking into the lagoon. The water going away from us above that zero. So all the blue is going away from us, and the yellow and red is coming towards us. So this is an inverse estuary. And this happens during the summer or close to the summer, when intense evaporation causes a hypersaline situation here. The salinity inside the basin is much higher than the adjacent Gulf of California. And then in the winter, you have a normal type of estuary. All this green and yellow is water coming toward us, and the blue is going away from us. And in this case, it's not driven by density, but by the wind. The wind drives this type of circulation. So it has tremendous implications for the water quality of the basin. This water is horrible in the summer, and it's not that bad in the winter. Why do you think? Yeah. You can see it and smell it. In the summer, it is horrible. Why do you think? Any pollutant that stays near the surface and comes into the bay, what's going to happen to it? How can it go out in this situation? On the mean, the water is going in at the surface and out at depth, so it gets trapped in there. It doesn't go anywhere. And in the winter, it gets pushed out of the basin by the wind. So that has tremendous implications. They have a fish processing plant here. So in the summer, all the discharges go in there and get trapped in there. And so in the summer, it just goes out. So I think it's quite important to understand this in order to be able to plan where you install these types of industries. But obviously they didn't know. But the more we study these systems, the more we find out new things. All right. And here's another type of estuary, a fascinating type of estuary that's called the salt plug estuary, in which the evaporation is approximately the same as the river discharge. I don't know where those glasses come from. Probably the Korean transformed my approximately the same symbol to glasses. So in this type of systems, the evaporation is approximately the same as the river discharge. And they're fascinating because they're a combination of a regular type of estuaries and inverse type of estuaries. Think of this is in northern Australia. And we have an estuary here coming out to this gulf. So the estuary, this low salinity water, increasing salinity, and then between station 2 and 3, you have the highest salinity. So salinity increases, you have the highest salinity here, and then it starts to decrease again. So in this area, you have what's called a plug of salt. Because of evaporation being almost the same as the river discharge, you have a regular estuary here. But because of evaporation, or in this relatively shallow area, you have accumulation of salt. So you get a salt plug. So looking at a cross-section from 1 to 2 to 3 to 4, you have this cross-section here. 1, 2, 3, and 4. look at the isohaline. You have a local high salinity of 37 right there, between stations 2 and 3. So that creates a salt plug in the sense that from here to the left, you have a regular estuary, salinity increasing seaward. But from here to the right, you have salinity decreasing seaward, so you have an inverse type of estuary. So think of a pollutant from this area and from this area. So this area will be in bad shape. That's where everything will accumulate. So that's an example. These are more difficult to observe because you have to have some river discharge and very intense evaporation. But the example is there. I got it from. I recommend that you look at that at the website. You can actually link directly if you click there. I can't because I'm not connected to the network. But if you click on that from the class website, if you look at the presentation from it, you'll be connected to. These are researchers from Australia who describes these systems very nicely. Any questions up to here? We're going to continue a little bit to set the framework under which we're going to study estuaries quantitatively. So up to now, we've seen what an estuary is and qualitatively what they look like and how we can classify them. So now we're going to establish a framework under which we're going to study the estuaries qualitatively. And for that, first we will do a review of the hydrodynamics